Anyway, we're going to make a start. So good morning, good afternoon, good evening to those that have joined. This has been an unprecedented interest in this electrical safety PPE webinar that we are going to be hosting here today. So thank you for spending the time to join. And one thing I can be sure of is that there will be no disappointments. We've got an extremely content-packed workshop that we're going to be moving through like a train. It's a recorded event which you will all receive afterwards, so you can maybe run it slower and digest. But this obviously is part 3 of our electrical safety compliance series that we've been running for a number of months now, and the attendance has been incredibly popular, and I think possibly down to 2 reasons. One of them being as the quality of speaker and the content delivered. The second thing being is the fact that they are truly non-commercial and unbiased events. So on this session today, there will be no products, no organizations, no services promoted. You may say it is what it says on the tin. So today is truth about outflash situations, the physical protection, so the correct equipment to be wearing, legal protection, correct tools, etc. There's video content. So I want to keep on moving. Quick ground rules. So the kids have started vacation this week, so I thought it was better for my wife that I escaped to the office. There's a total of 3 people here in the head office today because most of us have traditionally been working from home. But Ben and Anthony and Hugh are working from their home environments. I know certainly Anthony has younger ones in his house, so if you hear banging of doors and a few kids crying here and there, then please excuse us. It's the nature of the situation we're in. But
try to keep the noise down.
We're going to have fun today. There's a Q&A button at the bottom of all of your Zoom webinar panels, and we'd encourage you to click that and just put in any questions that you may have throughout the event, and we'll try and get to them to answer the questions that you put in. Any questions that remain unanswered will be answered after the event. So I'm Angus Long. I'm a Global Account Director here at Scanware. What sums me up, what sums the organization up? Saving lives. That's the people that work on or near live electricity, wherever they are in the world. That's the purpose of today's session. So Hugh, over to you, including your introduction.
Thank you very much. I'm Hugh Hoagland. I work for Arcware, which does arc flash testing. We do many of the arc flash ratings, and I've been doing this for about 25 years. We don't sell PPE or anything, and I also work for eHazard. We do electrical safety training and engineering work. And so we're going to go straight into the information. So truth about the arc flash incidents. And this is an important thing to understand. Arc flash has really raised the awareness in electrical safety. And in the US specifically, we have cut our fatalities a lot, and we'll talk about that a little bit more. But in the UK, since many of you are going to be here online from the UK, just looking at one country, they have about 1,000 average number of accidents in the workplace every year involving electric shock and burns. 25 people died in 2014. It's been 25 for several years now. I've been watching this for many years in the UK. Number of fire in England caused by electricity is 15,432 in 2015 and 16. And then there is a specific fine. You can be fined as much as 400 pounds. For a civil engineering contractor in 2019 on breach of electricity work regulations, the 1989 HSE program. So it happens in every country. I used to go around and speak, and people said we don't do any live work, but the most common way for an arc flash to happen is when you're making something safe in the process of de-energizing the equipment, or when you're working on equipment and you're doing testing. Those are the most likely times for it to happen, because that's common electrical work that is almost always done live because you're in the process of turning it off. Equipment failures are about 50% of the causes of arc flash, and 50% is human error. So there are different opportunities for that to happen. So these are our objectives for today, and we're gonna run through those. There's very few deaths from arc flash unless clothing ignites. So that's one of the things that we've been able to change in the US, and it started changing all over the world, is most electricians and most line workers in the US that work for the electric utility system actually now wear flame-resistant arc-rated clothing. When you just wear flame-resistant arc-rated clothing, almost all the deaths go away, but the burns can still be substantial. So unless clothing ignites or burns, most people don't die from an arc flash. They will die from shock, but they won't die from arc flash. So that one simple change of just going to daily uniforms that are flame resistant arc rated materials saves almost all the lives. And then when we match it, that makes a big difference. And you see here the statistics on approximately 50-50. There's a lot of different studies on this and there's different opinion, but it's around 50-50 equipment failure, human error. Work competence and timely maintenance really lower the frequency of occurrences. And so from an electrical engineering perspective, you want to do timely maintenance and you want your workers to be competent. And if those two things are done, many of the arc flash incidents go away. But then you can also lower them by engineering, but we're focusing on PPE in this particular class. Arc-rated clothing lowers the risk and the level of injury. So, and many times, if you have on arc-rated clothing, you get no injury at all, but the level is always going to be lower if clothing doesn't ignite, melt, and drip. So where do these incidents happen? Well, a common one, and I've done 200 accident investigations in the US and one in South Africa and one in New Zealand. So in doing those accident investigations, I found one of the most common places for workers to be really hurt is working in metal-clad switchgear. And it's primarily in racking in or racking out the switchgear. There's no shock hazard here, but there is a possibility that the stabs are misaligned or broken, or that there is a rodent or something inside of these. And that can cause the equipment to explode. And that is a very common place for people to be hurt. Another common place is overhead line systems. Even though this worker, and this is a staged accident reinvestigation where we blew up the piece of equipment again with the worker, a mannequin wearing the same clothing in the right spot. And the clothing was not touched, and the utility thought, oh, wow, this really was magic. No, it's because this worker was quite a distance from where the actual fire came. They saw the fireball, and of course this is a frame grab from the high-speed video. They saw the fireball and they thought it hit them, but it actually didn't get that close to them. So they just got some infrared radiation burn, which is maybe a first-degree burn, more like a sunburn. So just realizing that there are tools and things you can do to keep distance from the potential arc flash, they make probably the most difference in terms of never being hurt at all, is staying away from it when you can. But you know, a lot of the things people think could hurt them or think can't hurt them actually can. This is an accident investigation we did in Brazil for a company, and this gentleman was doing 120 volt control wire testing. So he was troubleshooting the control wires in the front of this motor control center bucket, as we call it in the US. And when he was doing this control wire testing, he moved one of the wires and it arced, but it was 120 volt arc. That's not enough to ignite clothing or even burn you unless you're touching it. And so what happened though was it arced back into the 480 part of the equipment, or the 600 volt part of the equipment, and blew it out in his face. So it went 3-phase 480 in the bucket because the wire was probably bad piece of insulation, is what we determined in our finding. So even though what he was working on was really low risk of arc and it was a low level of arc, it caused something else that wasn't properly protected to blow up. So it was an older style equipment, probably built before 1991. Meter bases in the US have a substantial, even though you can de-energize these stabs here, the bus is still energized and it's not insulated typically in the US. So if your bus like this, or any type of setting, even if it's not a meter setting, if you have parts that are energized while you're working and parts that are de-energized, if anything can break, and what happened was a stab broke off of this meter base, or the meter itself, and fell into the bus work that was energized, even though the stabs were de-energized, and it blew up and burned this person's face. And we'll show you what happened to him a little bit later. When we look at arcs are very focused events. And this is something that most people don't understand about arcs. They see a video of an arc and they think, well, it was a huge fireball, and it is, but most of the energy is in a very focused area. So the fireball itself doesn't cause a lot of burns and may not cause any burns at all. It's more theatrics after the arc, because the arc is the part that is the plasma and the part that is pre-plasma just outside of the arc. So in an arc that, like when we do testing, the arc is maybe a third of a meter long, but its effects are probably in about 4 times that area. So this is an arc that we did in a laboratory. We were replicating an accident, and we were looking at switchgear that could blow the energy out the bottom, and we were looking at a specific suit. And so if you'll look at this in the particular garment here, this garment's an 80 calorie long coat with leggings and non-flame resistant pants underneath. The trousers were non-flame resistant denim jean. They caught on fire, burned the mannequin up. Is a wonderful time. But you can see that only 25% of the body was actually hit by that 80 calorie per centimeter squared electric arc. So arcs are very focused events. So all of the clothing needs to be flame resistant arc rated, but most of it won't be hit with much energy. That's why you don't want to overdress in an arc flash event, because if you overdress, then you're just making a person uncomfortable when you want the PPE to be right in the right area. And so sometimes that's the front of the garment, sometimes that's the back of the garment, but the way the standards are written, you have to do it all the same. So we just recommend that you match it to the hazard. In the case of the next garment here, I put in a flame resistant garment underneath. And yep.
So I think that's a really important point that you raised there. So it's a bit of a myth to think that arcs will only ever come out at the chest area. So some organizations may choose to, wear regular polyester cotton clothing and then put on like just a cape or just a jacket just for the top half, because that is apparently where arcs will ever only exist, or it won't really be at the back, it will only be at the front.
That's totally a myth. I've investigated an accident where a guy was wearing a long coat. He was wearing a pair of blue jeans. The blue jeans caught on fire and burned up into the long coat. So that's absolutely a myth. You have to really look at the physics of the equipment, and you have to think about where the arc can be. We just recommend that everything be flame resistant arc rated, and that way you never have an ignition, because ignition, you pay $50 or $100 or say 200 pounds for a cape, and then you burn the blue jeans off the person. Well, you just wasted all that money on PPE, because now you've killed a person, but you bought a 200-pound jacket for them or something. So yeah, it's absolutely a myth. And so arc around 10,000 degrees Fahrenheit, which is around 5,000 degrees C, is the temperature of the plasma. It can be a little bit more, a little bit less, but that's typically plasma and air. But temperature of plasma is not what's really important. What's really important is the plasma density. And the plasma density at the roots of the arc is very high, and the temperature is high. And then as you come away from that arc root, it's going down in temperature quite dramatically. The infrared piece is going down in its total energy, but the hot gas ball is going down in temperature. But a third of a meter away, you can still be at 2,000 or 3,000 degrees, which is more than enough to ignite any clothing and melt any clothing. The plasma density just gets lower and lower until it becomes pre-plasma. This is an arc flash and an open air arc. And this is using our high-speed camera at the laboratory in Toronto. And what you're seeing here is only half of the energy, because you're only seeing the hot gas ball. The convection in this particular arc is probably around 60% infrared and 40% convection. So the infrared is completely invisible. You can't see it, but it only goes in a straight line. That's why the arcs are so focused, is because you get a hot gas ball and infrared. The infrared doesn't go around curves or anything like that. So it usually only hits one side of the body, and it only hits in a fairly small area, depending on the arc flash. But arcs can be totally different than that test. That test is designed to be very repeatable. Arcs like this, we call this an ejected arc. And this is one of the papers I did in IEEE many years ago. And this is where the plasma is actually shooting out toward the worker. This is a really rare occurrence in real life, but it does happen when you see a stab pointing out like a switchgear. If the stab is pointing out rather than pointing down, the arc is going to come straight out toward you. So understanding the physics of the arc and understanding how your piece of equipment is going to relate kind of helps you know where to stand, and it helps you know where most of the energy will be. Here we ignited this cotton t-shirt, burned the whole back of it off in 45 seconds because that was a really ejected out arc. But again, that's really rare. Most arcs are more like this, where they are coming out of the piece of equipment. And I think I've got this video didn't connect, so I apologize for that. I think it's trying to connect, but it's not connecting. And I'm going to try to go to the next one. Let me get over here. Oh, my PowerPoint shut down. Okay, that's fine. It does that once in a while. I'll bring it right back up.
The PowerPoint's struggling to keep up with you, Hugh.
Oh, yeah.
No,
I'll go back to that next slide and we'll look at, see if that video's there. Yeah, that video.
I'll repeat what I said at the very start. There is a huge amount of content. Hugh's moving through this very fast. The recording will be available afterwards. Keep going, Hugh.
Yeah, and we'll have a PDF for you too. So the arc in a box, all the energy is focused because the piece of equipment is focusing it. Then this is an overhead line type arc, and this was an accident replication. This person's flame resistant shirt had a couple of holes in it. It was completely scorched underneath the clothing, and the t-shirt just disintegrated, and the company was thinking that the shirt was the problem. And I said, no, it's because this person actually touched the power line, and the arc went underneath the clothing. And we did this several times, and one time we blew the shirt off. It came off the person's arm and wrapped around the power line because of the energy underneath the garment. And you can see here that we wetted the middle area there that's still yellow, and that area looks better, but it actually transfers more energy because the sweat will transfer the energy through better than the dry air that's underneath the part at the top where it scorched the garment, looks worse, but actually there would be less burns underneath there, no burns underneath there. So when we talk about a calorie per centimeter squared, that's not a real common unit even in the SI world. It's a good unit though to use because about 1.2 calories per centimeter squared takes you to right at the edge of a second degree burn. It's about 2 calories in an arc. It's about 1.2 calories in a fire. So that will take you to the point of second degree burn, which is still curable burn. That's what we're trying to prevent, is you getting much burn that's not curable. We don't want any of that, and we want to have very limited burn in any other area. In the US statistics, I like to point this out because one of the things that we see is that the people who get hurt in electrical accidents aren't always the electricians. Sometimes they're maintenance people, average maintenance people who happen to be working around electricity, or people doing construction and excavation. Construction and excavation is one of the top killers electrically because these people are not really trained about, but they're working around power lines or they're digging into power lines. And so make sure you include some of that in your training. In the US, we have about 1 person every other day dies from electric arc in a population of about 330 million. This is a great study from EDF in France. About 25 years ago, they did this study and they found that of their 120,000 electrical workers, 125 of them had electrical injuries every year, but 77% of those injuries were arc flash injuries. 21% were permanent disabilities, 2.4% were fatalities. If you look at DuPont studies, they found that almost all the fatalities were clothing ignition arcs or shock, and shock will by far be most of the fatalities. Permanent disabilities can be from the arc flash burns or from the shock destroying tissue and hurting people like their arms or things like that. So there's a lot of things we can do. When we look at overall safety structure, and this is a very simplistic model from the 1930s, but I like to use it because if you have 300,000 at-risk behaviors in general safety, you're going to have 1 fatality. In electrical, if you look at that study from EDF, 10 recordable injuries, something that you would put down on the paper, is going to lead to 1 fatality. So electrical incidents are not nearly as forgiving. It doesn't take 10,000 at-risk behaviors to lead to a fatality if you're doing at-risk things like not wearing arc-rated clothing or not using rubber insulating gloves or proper equipment or proper techniques. In the US, our statistics show that it's not the beginners, it's not the survivors, my age group out here, but we call them the cowboys. And it's because of three things. First of all, this Canadian study found that the average person that died in Canada in the workplace was between the age of 25 to 35. They were relatively experienced. Number two, they were above average intelligence because they know what they can and can't do. And they make the wrong decisions sometimes because they think they're smarter than the rules. The third thing is they are an extroverted personality because they have a desire to please both their fellow workers, the customer, the employer, and so they'll take more risks. And characteristically, they are male because males on average have higher testosterone, and testosterone hormone leads us to be more risky, and also it kicks in that machoism, and that's a cultural thing, but it's also a physiological thing where we tend to be more of a risk taker, and that's a role. Obviously, some males are higher testosterone, some females are higher testosterone, but testosterone does have a risk component that goes with it. So the higher your testosterone, the more likely you are to take risk. And so that's why more of the people in that 25 to 35 age die. Physical protection, correct electrical safety PPE to wear. And we're going to talk about this a little bit. So the first thing is polycot and cotton are both killers. And that is, if they ignite, you have about a 50-50 chance of living. And they really cause a lot of injury really fast. We used to believe that cotton was safer, but I found a study that basically showed me there's a 3% difference in survivability between cotton and polycotton. The reason that we always think cotton is safer is it's a little harder to ignite, but once it ignites, it burns hotter than polycotton. It doesn't melt into the skin, we used to think, but actually it's percentage body burn that makes the most difference. And here's the way it works. So if you're looking at the two factors that determine if I'm going to survive in a burn incident, here's the two factors: percentage body burn across the top and the age group. And we can't control age, but let's look at my age group, 50 to 59. I'm getting ready to leave this group, have no idea what my statistics will be next year, but here's what my statistics are now. If I'm wearing ARC-rated clothing, I have a 95% chance of living, even if it's not perfectly matched. Even if I didn't get the suit to 50 cals, I only wore 20 cals. And the reason is because now I'm not going to ignite the clothing, and you saw that arc, that 80-calorie arc only hit 25% of the body. Well, if the clothing doesn't continue to burn and take the burns elsewhere in the body, you only get 25% body burn, so you statistically are only going to get a 5% chance of dying. Now, if it burns your face or your hands, your life will be changed. But if it doesn't, you're probably going to be okay and be able to really be easily, I mean, even if it's not perfectly matched, if it's perfectly matched, you should get no burns at all. But if clothing ignites, say a shirt, or if a pant ignites, you're going to have about a 60% chance of living at my age group. And if you ignite your shirt and your pants or a coverall, you're going to have about a 20% chance of living. And at 50% body burn up, the quality of life drops dramatically. There's a lot of statistics on that I'm not going to go into. Melting clothing is obviously the worst thing, but flammable clothing is what really causes most of the injuries. In terms of arc rating principles, the non-arc rated layers are allowed underneath. You can wear a cotton shirt underneath in most of the standards and most of the work practices. The problem is that those can also ignite at some point. So if you have an arc rating of 8 and you get 20 calories, will you ignite a cotton t-shirt? Almost every time. And if you ignite a cotton t-shirt, it's almost as if you didn't have on the arc-rated clothing. So you have to be really, really careful that you match it to the hazard. If you're going to allow cotton clothing or melting clothing, you never want to wear melting clothing underneath. Layers of arc-rated garments can provide additional protection, but only arc-rated systems count, because you can't take 8 calories and put it over 4 calories and know you have 12. You actually might still just have 8 because of the way the physics works. And then the last thing is putting on a high visibility garment that's only 4 calories on the outside doesn't lower the 8-calorie shirt down to 4 calories. It's still going to have its 8 calories. And so I recommend those high visibility garments, unless they're your main garment, be as lightweight as possible, because you don't want to sweat any more than necessary. Eye and face protection in the U.S., this is just the way it's set up. I'm not going to worry about that, but I just threw it in there in case you're interested in how we do things. We allow a little less protection for the face so that people have good visibility, but that's in the utility systems. In the non-utility systems, you match it to the hazard just like you do the rest of the body. I've done a lot of testing on face shields, safety glasses, eyewear, things like that. They're all going to help you until they start to melt, but it's going to be a really high energy level before you're going to melt a normal hard hat. So always wear those things if they're required by your standards. There's also some belief in the past, and this is, I don't think I actually published this as a paper, but we did a fairly extensive study of balaclavas by turning the mannequin around to see how much energy, and we found that the worst case scenario was just hitting it right in the front. So if you turn it to the side, it takes 12 calories to get around that face shield to get burns. And if you turn it all the way around to the back, it takes 30 calories to get all the way around that face shield to cause burns. Because remember, you're only 50% or less convection. Most of this is actually infrared. I'm not going to show this goggle balaclava setup, but that can be work in some situations where it's cold. In terms of gloves, we do arc rate gloves now. We're working on an IEC standard. I don't know if this one's going to lock up on us too or not. Let me see if it's going to run. Oh, it's saying the media can't play. Sorry. Some of these don't play when you're set up online, but this one, I'll show how the gloves work at some other point. Okay. In the US, we use ARC categories or CAT or HRC, I think was the old terminology. I like to call them ARC, but most people are calling them categories now. It's called the PPE categories. 4, 8, 12, or 4, 8, 25, and 40 are the most common, and that's in a standard called NFPA 70E, which is used around the world somewhat because of US multinationals. But most companies use an ARC level 2 or a category 2 and a category 4 garment setup. And this is a good way to do it. If you wanted to stick one in the middle at about 20 calories, that would keep you out of the flash suit or as heavy of a flash suit more frequently. But this is really the best way to do it. And layering up can really add a lot of value because you can put a coverall over top of your 8. And if you match it up right, it typically works out to be around 20 to 25 calories with just adding a coverall to your 8-calorie uniform. So that's a good way to get up to quite a few calories and then put on the flash suits for the higher levels. We typically recommend that companies, if you're going to allow, t-shirts or undergarments like briefs or anything like that to be worn underneath the garments, that they all be 100% cotton or at least as much cotton as you can. But it's always better from an upper torso perspective to wear an arc-rated type t-shirt. When you're looking at PPE, also make sure that the label is correct. We find a lot of manufacturers that are just going over, they're buying a container load of something, they're having it made by somebody who has limited experience in making flame-resistant clothing. They'll frequently have an incorrect label. And so I always tell companies, these labels are from companies that actually have the right garments, the right fabrics and everything, but the company who's making and selling it, it's not very knowledgeable, and they have errors on their labels. And so I tell people, watch out for that, because that might mean that they don't have good quality control in the background if they can't even get the label right. Just be very careful. Not using arc-rated undergarments. Arc-rated undergarments, this is silk long john from LL Bean. And I'm going to show you that silk doesn't ignite and continue to burn. And so it's almost as if it's arc rated, but it's not very protective. So that's one of the negative sides. But if you're going to wear undergarments, silk, cotton, and wool would be your best undergarments because they naturally have some level of flame resistance, not so much from the cotton, but the wool will put itself out, the silk will put itself out relatively quickly. And then fall protection gear. You don't have a standard in Europe right now. The IEC committee doesn't have a standard yet. I've been asked to write one, and I've started on that. Can't play this media either, it says, but this is a fall protection harness. If it's been tested to about 40 calories, they work up really well. And there's quite a few companies in even the UK that are manufacturing these, and you can buy them. Beware of anything that says it's flame resistant. Flame resistance doesn't really have great definitions. And so there are things sold as flame resistant in the US, they're sold in Europe, that are flame resistant treated polyesters that really don't do well. And you can have a good polyester. There's some really high quality materials that are coated rainwear type materials that use a little polyester, but be really careful when something is 100% polyester and it says it's flame resistant. It really isn't from any of the standards that we want to use. And that one's media is not going to play either. I think maybe these are disconnected because it crashed, but that's okay. We've seen some explosions. This one, the explosion catches one winter wear on fire. The other one doesn't catch on fire. They look the same. One is flame resistant, one is not, but the only difference is the type of materials, and they are much more expensive, but they're much higher quality because they don't ignite and continue to burn in an arc flash. And I think this will be the same way. Apologize. So this one, we show how 100 milliliters of hydraulic oil will burn for about 5 minutes on the front of this jacket. We also point out that, I think this one will play. So this one is Deet. And the Deet here is just a common chemical that's used for mosquito repellency. And it will burn for about 7 seconds if it's soaked. And I mean, that shirt is soaked. We recommend using permethrin type chemicals. I don't know if your country can have permethrin, but if you can have permethrin, it's a water-based application. It leaves very little chemical behind, and it kills ticks and mosquitoes. And we recommend you do that, and then use Deet wipes only on the skin to keep away insects if that's an issue in your country. Also, in terms of how do you wear things, we recommend you to tuck, button, and roll. And so if you could watch this video, and this is one that won't play, we actually ignite the t-shirt underneath the shirt because the worker didn't tuck the shirt in. We also recommend you roll the sleeves down, you tuck the shirt in, and then you button up the top button that you can so that you protect all the skin that you can when you're wearing garments. So how you wear the garments makes a difference too. Let's see if this one wants to play. I think that one will. This is it's a disposable type garment for arc rating. These are a wood pulp material. They're sold commonly in the US, and I know that they're available in Europe. This wood pulp material is flame resistant, and it's a natural fiber, a cellulosic fiber, so it won't continue to burn and it doesn't melt. And it's a disposable type garment that has a very low arc ratings, but they can be used for over top of flame resistant materials if you're gonna get oils on you or something. So you take those off because hydrocarbon loading can add to your burning, as we saw with that hydraulic oil. So layering, the outer layers need to be flame resistant, arc rated. The under layers need to be arc rated or non-melting. You want to cover as much of the body as you can, fit it comfortably, and follow the manufacturer's instructions on washing. No chlorine bleach, no fabric softener is the typical recommendation. One time with a fabric softener doesn't take out flame resistance, and some materials are not really affected by fabric softener. Just check with your manufacturer and see what they recommend. But if you ever have questions, you can certainly talk to us about this. We've got about 3 papers on bleach studies of different fabrics, so it's pretty interesting. This one obviously won't play, but I'll just tell you what happens here. We hit a 40 cal suit, and we hit an 8 cal suit with a cotton t-shirt underneath, and we completely ignite the cotton t-shirt underneath. So going over the arc rating of a garment and wearing flammable material underneath really raises your risk. It's always better either just to wear the flame resistant arc rated garment and or put a flame resistant garment underneath if you have any chance of going over the energy that you are predicting or that the clothing will protect to. So legal protection, correctly identifying these things. Let me look at my timing. I'm in good shape. So in terms of legal protection, this is the EU PPE law. And I'm not going to go into detail here, but it requires you to get PPE that will protect you from the incident heat flux. And so this, I think, applies to arc flash. It applies to flash fires. It's basically telling you to look at this. It doesn't give you exactly what you've got to do, but much like the US laws and OSHA, it tells you protect your people from hot splash products, protect them from incident heat flux, coefficient of transmission, find a way to make sure that clothing doesn't catch on fire. All these things are required by European law. So legally, you have to protect your workers. And if you know there's a hazard out there and there are international standards on these hazards, you have to protect your workers, even if the EU doesn't give you direct guidelines on exactly what to do as much as the US law does. If you want to look at a really, I think, well-written law, we've been very fortunate. We've had an electrical engineer in our federal OSHA for many years who's just a great guy. He's now retired, but he wrote OSHA 1910.269. 1910.269 is all the regulations, safety regulations for electric utilities. And many companies have taken this and emulated this document in their national regulations. We've certainly picked out things from the UK. We picked out things from the German standards and others in order to make sure that we had lots of input on this law. And so it cites IEC standards, it cites some ISO standards, and it also cites a lot of ASTM standards, which tend to be our national standards, although ASTM is international now. You can also look at IEC 61557-9, and there's some other related IEC standards. The IEC standards typically are to make your equipment safer to work on, which is a great way to do it. We have not done as much of that in the US. Thus our injuries a little higher. We're starting to go that direction, which I think is a very wise way to engineer out the hazard. But PPE in this case is almost engineered PPE because you match it to the specific hazard, unlike just putting on a hard hat that generically kind of protects you to things. It's a very engineered solution in arc flash, much more than it is in flash fire. So look at these standards, learn from other countries. We have a lot to learn from the European method of making our equipment safer, and I think the EU can learn a lot of things of what we've done with PPE. It's a good combination in my mind. The other thing is making sure your workers are very competent in their electrical work. This is something that people accuse the U.S. of having a problem. In our utilities, we really don't. But sometimes in our general industry, we do. And as I've gone around the EU and gone around the world, I found that this is really true everywhere. The utilities tend to have very highly trained people. Their equipment is somewhat standardized. But when you get out into industry, you find a lot of people that are multi-skilled, and they don't have as much technical knowledge of electrical. But this is kind of our definition in 269 of what a qualified person has to have. They have to have demonstrated skills, training, and knowledge of that equipment. These are some things that are used in electrical standards that are part of your written safety program. In the US, by law, we have to have, every company has to have their own written electrical safety program. They can't say, we just follow the law. They actually have to have documented ways of doing this, kind of like part of their ISO 9001. If they have that, it's part of their safety. It's built into their 45000 series or their 1401 series. If they're doing ISO certification of their processes, if not, they use the ANSI standard listed there. Arc flash boundary concept, you'll find in the US, and this confuses people sometimes, in our electric utilities, the boundary starts at 2 calories, and in the non-utilities, it starts at 1.2. It's difference between a Duke Energy Power Company study on second-degree burn in arc and the Stoll curve, which was done with flames. And so it does take a little more energy to burn you in an arc than it does in a flame, but 70E uses that 1.2 to be a little more conservative. And so if you're looking at standards out there, there are 3 different types of standards around electrical PPE. There is work practice standards like a 70E, Z462, and these IEC, IEEE standards that you see at the bottom there in the blue, and blue or purple. I'm sorry, I'm a little colorblind. In the middle there in the green, we have testing methods, the vertical flame test and all those kind of things. And then over the other side, you have your specifications. And so you want a specification in the garment. We see in some countries, not so much in the EU, but we see in some countries where they just put a test method and some criteria in the garment, and you really don't know what you have. So you want to have a specification if it's available. These are some regulatory bodies that set standards. Obviously, you're going to have BSI standards, you're going to have German standards, you're going to have Dutch national standards, you're going to have EU regulations. Also, IEEE, IEC, ISO, NFPA, and ASTM are all leaders in this electrical safety and arc flash lab world. Our laboratory is an ISO 17025 accredited lab. You want to make sure your data comes from that. If it has a CE mark, it has to. So when you have a CE mark, unless it's faked, it really has to have laboratory data, and you can ask for that data if you want to. These in the CE marks, the great thing is you actually have a 17065 accredited body who is certified arc flash PPE. It's level 3. So it has to be certified, and the garment's certified, and the plant is certified. So it's a fairly rigorous process, not quite as rigorous as the US third-party certification in NFPA for firefighting, but it is it's much better than our arc flash standard. So look for that CE mark from a reputable lab, and you will find that you get pretty good compliance. And this is kind of the EU regulation there I just included. So correct tools and how to use them. So first of all, anytime you have a dielectric hard hat, it needs to periodically be tested. You squeeze it to make sure that it doesn't have a snap, crackle, or pop. And if it doesn't have that snap, crackle, or pop, that hard hat's usually good for 2 to 5 years. So in the US, we recommend that you replace the hard hat support, the suspension inside, every 2 years. And we recommend that you replace the hard hat every 5 years, though some manufacturers recommend every 2 years. If there is a recommendation from the manufacturer, obviously follow that. But those dielectric hard hats, typically made out of polyethylene, are really protective from shock. And that's always a really good thing to have on. There's our snap, crackle, pop test there. Electrically hazard rated shoes. This is relatively new. It's just coming out as an IEC standard. I don't think it's quite finished yet. There is a US standard, and you can see those standards there. ASTM is ASTM International. You're certainly welcome to use that standard in your company's requirements. I don't think European law would let you use it at this point, but they're still working on MOUs. You know how all this stuff is, that's politics. But the ASTM boot standard is now being flipped over into IEC without violating copyright. So they're taking the performance characteristics and writing that into IEC, but those are available out there, and they're overshoes on the right there, and on the left, they're typically, the soles are rated. This is both a Canadian standard and an ASTM standard, and this is, the soles are rated for electrical shock in case there's electricity in the ground, like when a downed power line is nearby, or if something's not properly grounded. Insulated tools need to meet the, I apologize, I have the ASTM standard here. There is an IEC equivalent. Actually, our standard copied yours. So in this case, we went the opposite direction, which is pretty common. We'll go back and forth. But this standard makes sure the tools are insulated. But in the IEC and the ASTM standard, we always recommend you use a 2-color system. And here's why. If I see yellow in this tool, I know that the tool's outer surface has been scarred up enough that now I'm past 25% of the insulation. I need to take the tool out of service. Otherwise, at 50% insulation, the IEC and the ASTM standards say you must take it out of service. Well, how do you know it's 50% insulation gone? So it's much better if you have the 2-color system. And in the EU and in the US, we typically, most of the companies make it with a 2-color system. I just recommend that. It makes it easier to know when this tool needs to be taken out of service. And then some ideas on how to store your tools properly, to prevent damage, make sure that the tools are, we like to recommend you separate the tools. Don't put them in a normal tool belt where they're scratching each other. This is an electric tool. I'll go back and show you here. This is a DuPont company, requires that every tool be in a kit like this, so you know that none of those tools are missing. Because if that tool is left inside of a piece of electrical equipment, it still has some conductive parts that could fall into the equipment by vibrating. It could fall in the equipment and blow the equipment up, which could shut down a refinery. So DuPont requires you to have it actually separated in a toolkit like that. But most companies don't. They put them in just stick them in a tool pouch, but then you're scarring those tools every time you use them. It's really good to take very good care of these tools. One, they're expensive, and two, they can be damaged quite easily. And then, of course, all these are hot sticking tools that are used in the US and used around the world. These types of tools have to be tested regularly. You want to make sure that they're, in the US, it's required by law that they be physically tested every 24 months and that they be inspected by a third party, not third party, but a second person who is qualified to determine if there's any scarring that would cause this tool to fail. And then, of course, they're inspected every single time you use the tool. They're cleaned and inspected. And so it's really important to take care of these and to clean them only with agents that are allowed for that particular device. See how I'm doing on time. I'm in good shape. Clean the tool thoroughly, verify the test date, and make sure everything is working correctly before you use them. You're inspecting for cracks, you're looking for defects, you're looking for deformities, electrical stressing, and proper operation. Tag damaged tools, take them out of service so they can be repaired, replaced, or destroyed. In some cases, they just have to be destroyed. And then all of your rubber goods, and we do glove in the US, and I know they started to do gloving techniques in the UK, just make sure that those are tested very regularly. We require by law that they be tested every 12 months and put on adequate cover-up. When I go out and investigate an accident when a worker has been hurt or killed with doing gloving work, it's typically because they did not put on enough cover up or they did not seal it in place with these clamps or things so that something doesn't come uncovered if they bump it. And so that happens from time to time. It's fairly rare in the US now. We have really, really high quality training in that area for our electric utility workers, but just making sure that that thing stays in place and that it's tested regularly. Inspect insulating equipment before installing it on exposed energized parts or equipment. You just want to make sure everything you're using really works. Okay, and then rescue. And rescue, it's required that you have rescue training annually in the US if you do electrical work. And this is typical that sometimes you have a on-site group that comes in and does rescue. That's fine, but many companies just train everyone on rescue. But the good basic rescue that everybody should know, and probably a tool that everybody should have, is a rescue hook. If you don't use this, use something else. Use a rubber insulating glove. Just don't try to pull that person off the electricity if they're hung up. Up to about 600 volts, a person can clamp onto it and be held onto it, but they are now energized. And so we frequently find somebody dying because they tried to help a fellow worker. It's best to use an insulated hook or to use your rubber insulating gloves to free them if you can't turn the power source off. But obviously, if you can turn the power source off, that's the easiest way and the quickest way to save them. And then using test equipment correctly. And again, I said earlier that improper use of test equipment is one of the big human error things and equipment failure things. So if you put a 1,000-volt meter across, in the US, we typically have a 4160 system, which is kind of a low medium voltage system. And you have something similar to that in the UK. You'll have a 2,000 volt, a 5,000 volt. I've seen, I think, 3,000 volts. In that case, if you put a 1,000-volt meter across that, it will blow up in your hands, and now the arc is right against your body. So that's a really bad scenario to have happen. So it's really important that you use the test equipment correctly and you have training. Our standards, our work standards, require annual training recertifications on meter use for workers to make sure they really understand how to do that. These are your meter standards in IC. We use these same standards. We have a UL equivalent in the US, and typically you're going to have your IC 61243-3 that will be your absence of voltage check tool. Make sure it meets that standard and make sure it's high quality. You don't want this thing to blow up if you put it across to higher voltage. We actually typically try to buy a tool that can take 5,000 volts, so that if it's put across the wrong voltage, it won't blow up. It'll just stop working. But some of these tools are that meet that standard, are very, very low quality. Some of them are really high quality. I recommend get a real high quality one. And then if you use a multimeter, you're going to use the IC 61010-1, and that's our UL equivalent, exactly the same standard that UL has an MOU on. And we recommend you use those. But they will not take, if they're properly built and meet that standard, they won't take 5,000 volts because they have to be really accurate for low meter use. We recommend to use an IEC 61243-3 for absence verification of voltage because it's just a safer device if you get it on a higher level. They're not all created equal. Get high quality tools. Make sure you're following the right standards. 61243-3, this one meets 61010. And also probes, we recommend you go for very little metal on the probe so you can't cause an arc with the probe, and the retractable probes, and if at all possible, fused probes. You can use those on the 2-pole 6143-3, you can't use them on a 61010 because it's gotten more accurate for computer level voltage testing in milliamps. So now you can't use the fused probes or resistive probes, but they are safer on the higher voltage type systems if you accidentally get them in the wrong place. We used to recommend a Cat 3 or 4 meter, but if you're using the dipole meters, they're not going to have those categories on them most of the time. And so those are the safest ones to use. In terms of a little research we've done, if a door comes off of electrical equipment, you have quite a bit of pressure that builds up behind that door. Is this saying it can't play? That one can't play. Darn, that's the best one. I apologize. So that one on the right, the door blows off and knocks down the 300-pound mannequin. On the left, it just basically puts out a hot fireball and the mannequin stays in place because it doesn't have any pressure because there's not containment. You need current and containment to get much pressure. The calories do not make pressure. It's the fault current, and it's really a very short period of time that it'll develop pressure. So you can blow a door off a piece of equipment. That's why typically you always operate to the side of the equipment. And this is an IEEE paper that you can get information on that I've published. All right, boundaries aren't just for shock. The boundaries also are for arc flash. Look these up, use these types of boundaries, develop your own company's boundaries. I don't see a lot of this in the EU except in IEEE 516, and that's used quite frequently. And then which one of these is the worst accident? Mark didn't wear his face shield. Second degree burns only, first and second. The black part is not charred skin. It is literally smoke soot from the arc flash. He was back to work in 2 weeks, but his PPE worked. He just didn't wear the face shield. All arc rated materials that he was wearing. Vitor filed a grievance against the company on his union because he was the union safety representative in Brazil. And he wore the arc flash suit because they said, until the grievance settled, you're going to wear the suit. He got 40 calorie suit that only got probably 30 calories on the hands, 15 calories on the arm, and 5 calories on the face. He got no burns at all. It really works, folks. Use the equipment. And we're going to go now to questions. If you have questions specifically for me, you can send them to questions@e-hazard.com. We will answer them, or you can pop them in here right now. And this is their upcoming webinars, so we'll start taking questions.
Thank you for that, Hugh. So as similar as we've experienced at the start of the webinar, we had a bit of a technical glitch. It dropped away for a few moments. So I didn't manage to finish my popcorn, Hugh. I was getting quite into watching the videos, you know. So I was missing a few of those, and a couple of folk have put the request to have access to the videos afterwards. So we'll see what we can do there. Ben, do you want to give us some of the questions that have come through?
Yeah, of course. There's quite a few, so I'll try and be quick with these. So the first one's from Gregory. How does sweat affect the ATPV or EBT?
What would you, Hugh?
Seems I've lost you here for a second.
Do you need me to repeat that, Hugh? Can you hear me?
Yes,
okay?
please. I lost it.
No worries. So this one's from Gregory. How does sweat affect the ATPV or EBT?
Well, it raises the EBT. It makes it more protective because it lowers the temperature to only 100 C in the garment until you burn off all the sweat. So it typically will raise the EBT of a garment, but it will lower the ATPV on some fabrics. It raises it on others. And we have a published paper on that. If you pop in a question or an email, I'll send that to you, or you can go to the eHazard blog, type in sweat, and it will link you to an article that links you to all the papers. I think one of them is published in the Professional Safety Journal of the American Society for Testing, or American Society for Safety Engineers, ASSP now, professionals. That one I think is online free. The other one is part of IEEE, and it's part of an IEEE membership where you can purchase it.
I think you, I think the point as well is being made is that any perspiration on the skin increases your risk of burn. And so the absolute recommendation is that you are doing all you can to mitigate the amount of perspiration sitting on the skin, and it's wicked away.
Yeah, that's the best thing to do, but it's more complicated than I thought it was when we first started studying it.
It's good. Ben?
No, next one. So the next one's from Richard. What was significant about 1991? I think this was quite earlier on in the presentation.
Yeah, I think if I'm not mistaken, and I've been on IEC committee now for 25 years, I think in 1991, the European law or the national law started accepting the IEEE, or sorry, the IEC standards that required bus work to be insulated and required basically equipment to be touch safe. And I think that happened kind of across Europe in 1991. So any equipment built before that may or may not have been touch safe, depending on companies' individual standards, but it kind of became law across most of Europe when that IEC standard for touch safe equipment started being used regularly.
Oh, great, thank you. So the next one from Justin. Why do companies test at 100 kiloamps and leave under UL standards?
That is probably so the equipment doesn't have backstream arcs. But those typical standards are for downstream arcs, don't blow up the switchgear. They're not so that the switchgear doesn't blow up, if I'm understanding what the question was. I'm not an equipment expert on the electrical equipment. I'm an expert on the arc flash equipment, so I apologize if I got that wrong.
Great, thank you. The next one's from Scott. The EDF injury statistics, statistics seem high. Are those numbers consistent with US electrical injury stats, including permanent injury percentage?
We're probably higher than that in terms of, well, the percentage is probably about the same. The EDF statistics were a 10-year study, and so that was before arc-rated clothing. So I don't know what arc-rated clothing played a difference there, but it was before arc-rated clothing, and that is pretty close. We see about a 10-to-1 relationship. There's more than one study. I think one is an ASSE study done by DuPont. It was a 13-to-1 permanent disability versus fatality. So it's probably pretty close. And that actually is the best electric utilities in the US have 125 electrical injuries per year if they had 120,000 workers, but that's the whole country of the US too.
I think we also should be mindful from a European and a North American perspective. So North America, large amounts of the utility distribution and transmission network is open just because of the sheer size of the country. In comparison to Europe, most of the utilities and distribution is underground. It's not exposed to the same kind of elements. So of course, the US statistics on arc flash injuries, typically speaking, are higher than Europe.
Yeah, we have about 75 deaths of overhead linemen a year.
Mm-hmm.
And that's, but that's for the whole country.
Yeah.
So we're 10 times the UK. So, but that's just the overhead linemen. And it's because that's all exposed to the elements, storms get it, all kinds of problems. Yeah.
Very good. So I want to be respectful of the time that we've committed for everyone. Thank you very, very much for joining. Up on here, I think it's critical to point out. So there's another 4 workshops that we're going to be running in the coming months. Again, totally non-commercial. They are, so the next one is inspections, audit, and accident investigation. This will have a much heavier European standpoint from a legislation perspective, albeit we are joined with the global head of investigation from ABB, which is good. Sorry, Hugh, can you just move on to the slide? Then,
this one.
if you just go back.
Yep.
Sorry.
Then we have one that we're running next month, which is focused on the wind energy sector. And then you can see the other 2 workshops that we have later on in August and September. Moving on to the last slide. So there's going to be a request for feedback. Please put your honest, candid feedback on how you have found the event. We need to get that feedback so we can continually improve the content and our way of delivery to make it as meaningful as possible for you. And but for every submission that comes back, there will be the opportunity to receive a template, arc and flame protective clothing and PPE policy that's kind of been evolved and pulled together over the last 4 to 5 years. So with that, any outstanding questions are going to be answered in after this event in a follow-up communication. We'll have a little Excel spreadsheet of all the answers, all the questions rather, and the answers that go with them. So we're gonna have to love you and leave you all now. Thank you for your attendance and keep safe, guys. Thank you.
Thank you.
The questionnaire should be on your browser now that you joined with.
Okay.
Thanks, folks.
Okay, Ben, I've made you the host again.
Thank you, Hugh.
Looks like
Can I
you're
close it
still
down there, Rob?
recording. Looks like you're still